Welcome to this Nexus tutorial. In it we will explain how to use the microcontroller library to create a timer and a PWM, extending the digital buck controller example. Let's get started with the timer. We will first of all create a header named hardware. And declare a void pointer that will reference the timer. We will also declare a hardware init function. Next, in a C file, we will define the pointer variable and the function, adding in it the timer creation. Now we will add the microcontroller library in the main file. Initialize it, as well as initializing the hardware, and add a periodic task for the microcontroller library. All the peripherals will be updated in it. We are now ready to configure and use the timer in our application. But first, let's redefine its callbacks to be similar to a real device. We will now have a background loop, which will be called from the infinite loop, and a control task, that will be called from the timer interrupt. Let's move this modification back to the main file and implement it in the application C file. We will declare the period of the timer, and use the library to configure it, passing a pointer to the control task as interrupt handler. Let's build it and run the simulation. We can see that the behavior is similar to what we had before, and we can set a breakpoint in the control task and observe how time increments in the desired step. Now we will see how to generate the PWM signal directly from the controller, instead of sending a duty cycle value. Let's start by modifying the buck circuit so the DLL block output is directly connected to the PWM signal. Next we will create the PWM just as we did with the timer. In the hardware files, we will declare the PWM pointer and create it with the library. And in our application, we will initialize it with a period of 200 kHz. We will also modify the control task so it configures the PWM with the duty cycle calculated, by setting the falling edge event. We could now directly connect the output of this peripheral to the schematic model, but there is something to consider when dealing with high-frequency signals like this. The synchronization step, or even the step of the microcontroller simulation, are not small enough to provide all the detail needed in this case. So we will use an auxiliary PWM module that will execute at the Plecs model, and will be managed by the digital controller process. For that, we will edit the shared header and add a PWM link instead of the duty cycle. Next, in the controller main file, instead of writing the duty cycle, we will dump the configuration of the PWM peripheral into the link. And in the DLL source file, we will include the microcontroller library, declare the auxiliary PWM, and load the link from shared memory. Finally, we will use the simulation time and step to model the auxiliary PWM in the processing callback. We will now launch the simulation and check if the PWM is working as expected. Again we see the same behavior, and if we zoom in the PWM signal we can measure a time step of 5 microseconds, matching the 200 kHz that we configured in the controller. Thanks for watching. If you liked this video, hit the like button and subscribe.